yesterday you guys redid that calorimetry lab, and you noticed, and it was really good this time. I appreciate that. You noticed that heat flows from hot to cold, and you guys were able to do the math and figure out the specific heat of your metal sample, and it looked really good. Okay, now I'm interested in one more thing. We want to look at how temperature changes in a phase change. Okay, and so if we did this lab in Science 9, if you take temperature versus time for a sample of water, and you take your water, and I'm gonna move this down, and you start to freeze it, and you measure the temperature as it starts to freeze. The temperature starts high, up at room temperature, and you start getting it colder and colder and colder and colder and colder and colder, and it eventually hits 0 degrees. And you're still making it cold, but it just stays there for a while, and then it'll go down again. Okay, so this is 0 degrees Celsius. Then if you take that same water and you heat it back up, it'll go up, 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 up to 0, and then it'll hang out there for a minute, and then it'll keep going. Right above the line, this is liquid. Below the line, this is solid, the 0 degree mark, because this is the freezing temperature, but it's also the melting temperature of water. They're the same temperature. So is there a difference between the solid ice right here and the liquid water right here as far as the energy goes? What is this pause all about? Well, it turns out there is a difference. The difference comes in particle arrangement, right? A solid has all the particles lined up in a nice orderly crystal structure. A liquid, the particles aren't in that crystal structure. They can slide around, move past each other, and so there's disorder, right? To go from here to here or there to there, energy is changed, and it's not a temperature thing, okay? Because temperature has to do with the average kinetic energy of the particles. This is a latent heat, they call it. You can't measure it in a temperature with a thermometer because the particles themselves aren't gaining or losing kinetic energy. They're gaining or losing potential energy. It's this particle arrangement that's shifting, and that does require energy to get something to melt, to go from this ordered to disordered. A little bit of energy has to be taken in, or to go from disordered to ordered the other way, a little bit of energy is released. Okay, and we're interested in how much energy it is, how much energy is required to melt ice, or how much energy is released when ice melts. Okay, so you guys are going to do a lab today. It's got a step-by-step explanation on it, but that's what we're trying to figure out. This is called the latent heat of fusion, or just heat of fusion, and it's the energy gained or lost, okay, when something melts or freezes. Okay, so energy gained or lost during melting or freezing when the temperature's not changing. Okay, now how can we measure this? Well, if we take a known mass of ice and we add it to some water, right? So it's just a calorimetry experiment now. We have our cup full of water. We know how much is in there. We know its starting temperature. We add some ice. Okay, and this ice needs to start at around 0 degrees Celsius because we don't want to waste heat trying to warm up the ice. We want to start with our ice at 0 degrees. We put some ice into this water. The water is going to cool down, but the ice is going to melt. And since the water is releasing energy into the ice, we'll be able to figure out how much energy was required to melt the ice. Okay, and from that we will be able to determine the latent heat of fusion of ice. Okay, the lab does have some step-by-step procedure stuff on it and some questions. Good luck.